Okay, so welcome back. The next eigenanalysis we're going to do is using the system stiffness matrix K that we've obviously calculated before, but then also the geometric stiffness matrix, which we're referring to as KG. And that's dependent on the loading we've applied. And so any of the results that we get, so the eigenanalysis, eigenvalues and eigenvectors, will be dependent on the load we applied in the original problem. So the first thing I'm going to do is I'm actually going to change the setup we have. So rather than the portal frame, I'm just going to construct a simple column here. So I'll go also and change my boundary conditions. So down at the bottom, I want it pinned, but then up at the top, I'm just going to restrict the movement in the X direction, and I'll just alter the load up here as well. So if we just have a quick look at our nodes here, you can see that's basically what we're looking at. So these boundary conditions are all appropriate. So the step that we need to do here is obviously we're going to use a lot of the information that we had from our original stiffness method component. But what we need to do beforehand is we need to establish what the change of length has been for each of our elements. So to do that, I'm going to, as I often do, I'll have to pull across my original node points. So we'll just label them up like so. Then I want to bring in my unscaled, so quite important that it's unscaled. So my unscaled vectors, I'm just going to turn the bifocals off. So unscaled displacement vectors, and then the final bit, again, what I often need to bring through, so I can just explode the tree straight away here, but I'm bringing in obviously the original element nodes as we had them. So I just call that element nodes in there. So we'll go and just find the original nodes. We were just looking at them over here. So I'll bring that in there. Again, just to keep things reasonably neat, I'm actually going to turn off the wire there. So we'll just do that as hidden. For the displacement vectors, they were outputted from here. So you can see this is before we've done any scaling. So those are the unscaled displacement vectors, and I'll actually also just turn that off for the wire display. And then finally the element nodes back to this matrix over here. So we have the start and the end nodes. So we'll just bring that across here. And then again, I will just turn the wire display off there. So set that to hidden. So just moving my nodes then. So feeding in the original nodes and the unscaled vectors. Then obviously we can select the list items. So in this case, my list is the scaled components, or the displaced nodes rather. So list item again. bring in there, just turn off the wrap as usual, so we don't want any of the data accidentally wrapping around, and then feed in obviously the start node, end node like so, and then we can put in the line is just what we're constructing here, and now what we want is we want a length. So there's a few to choose from, but it's this length here, and that just measures the length of the curve there. So I'm just going to label this, so I've grouped it, and I'm going to call that displaced element lengths like so. And then what I want to bring across is obviously the original element length, so I'll just bring that across as a number, so original element lengths there, and these are going to come back way back from here, so when we define the vector for each of the elements, so I'm just going to bring that over to here, and again, I can just hide that line if I want to, so I'm going to do that. So wire display hidden, and obviously to calculate the change in length, what we want is the new length minus the original length. So you can see for the particular load setup, all of my elements have got a little bit shorter, so they've all gone into compression. So I would just group this now, like so, and I'll just call this calculating the change in element length. And obviously, because I've been working in millimeters, this will just be in millimeters like so. So I mentioned that actually a lot of the information we want is going to be the same information that we had originally over here. So I'm just going to select this whole group, Control C, and then Control V, and just undo that drag. So I'll just try that again. I'll just actually select the group with all of the components in it. So Control C and then Control V. So you can see we've got a nice copy of everything there. And I'm just going to drag it down here. Obviously, there's quite a lot then in here that we don't need. So I'm going to say, I'm going to rename this. So I'm going to call it Eigenmode solution with the K and the KG matrices. So I still need my Young's modulus value, and I still need my area, but actually I can get rid of the second moment of area component. I still want my number of nodes and my number of elements, my element nodes, element lengths, element angles. All of them are useful to me when I calculate everything that I need to. I don't need the information on the point loads, and similarly I don't need information on element angles or this equivalent nodal action information that we had down here. What I will need though, so just tidying some of these relays up, so I do want my original K matrix from that stiffness method component that we set up at the beginning, and then the other information that I want, I'm going to call it delta L. So that's the change obviously in the element lengths. So I'll just tidy all of this up a little bit. And obviously add in two more relays like so, Control C, Control V. And then I will just tidy all of them up. So here we've got our change in element length, so I can bring that in. And then obviously from back over here, this is where we're getting our original K matrix. So just bringing that in like so. So on the other side, all that we're interested in outputting, so I can get rid of 2 of these in fact. So it's the eigen values and the eigenvectors that we're going to be outputting. So I'll just edit that there. So eigenvalues and eigenvectors. So what I want to do now is obviously just go in. So I've accidentally got some kind of issue going on with the grouping, so I'll just ungroup everything. Okay, so I will ungroup everything again, just sort out this, tidy them up a little bit, same over here, just tidy them up a little bit. So now I'll just regroup this, so group, and we're going to call this the eigenmode solution with K and Kg, like so. Okay, so obviously this is not doing anything at the moment because we have the wrong Python code in here. So I'll just double click, and on this occasion we can go Control A to select everything, and then just delete everything. And out here I've got my text file, which is what I want to bring in. But you can see what we're doing here is we're just generating the geometric stiffness matrix. So in a very similar way that we did previously for the system stiffness matrix. But the sort of line of interest is this one here. So that's actually just carrying out the eigenanalysis there. So I'll do Control A to select everything in here, then Control C, and come back into my Python component and Grasshopper here. So Control C I did before, so Control V in here, and hopefully everything will have sorted itself out. Okay, so there's just a little bit of an issue here. So I probably just need to adjust the input, how it's coming in. So this delta L, obviously this needs to be list access, and then the other information that we need to give it is that's float. K down here, so again we often have to do this, but we will just confirm that we don't want any type hint. For the eigenvalues coming out, so we already have that set to float, so that's fine. And then the eigenvectors we also want to set to float there. And then we did most of our work up here before, producing this grouping here. So I can just Control C, Control V, so bringing all of this down here obviously now. So we have our sliders as we want them. What I'm just going to bring in here is obviously want the eigenvectors now from this analysis. I can put up a panel here for the eigenvalues. So what we can see is we have some very large values here. I suspect I know why that is. So what I hadn't done was I hadn't adjusted back over here. So I'm going to take the depth back to 1. And what we'll see, so now we have some eigenvalues below 1. So that indicates that actually we're expecting buckling already under the load that we've applied. But we can do as we would normally do. So I'll show the original elements and the eigenvectors, and let's just cycle through the eigenmodes to make sure these make sense. So 0, that's the first buckling mode, so this is what you would calculate if you were doing Euler column buckling. 1, 2, 3, and so on. So this all seems to be working. What we can do is just to show again that everything's working. I'm going to alter the boundary conditions, so we'll actually just make it free completely at the top, but we'll turn it into a fixed condition at the bottom. And now what we can do is if we zoom back over here, we can see, so that first mode is as we would expect, second mode, and so on and so on, and also our eigenvalues have altered here, so we can see the first mode is very low. So if I want to address this, what I can do is, just to show it's the multiple of the load, I'm going to go in here, I'm going to set that load to basically 100th of the previous value, and then you can see all of the eigenvalues have adjusted accordingly. So the very final thing I spotted here, I just hadn't grouped these up here, so I'm just going to group them and give them a similar name. So up here we will just call this little lot, so this is the eigenmode solution with K, and obviously what we've been doing is we've just been producing the eigenmode solution with K and Kg, but we can maybe just have a quick look back here. So actually you can see that already this would have given us quite a bit of information. It's just the eigenvalues up here are not giving us the buckling modes, or rather they're not giving us the buckling loads, which the eigenvalues down here are. Okay, so I will see you for the final video shortly, obviously carrying out eigenanalysis, this time with the K and the M matrix, so the system stiffness matrix and the mass matrix. And as ever, just remembering to save back here, so we'll save that there, and I'll see you for the next video.